How's it going?
Good.
Okay, guys.
My money is going to pay you.
How's the weekend?
Good.
Good? Sorry.
Unless it is your fault.
It could be my fault. You never know. It's possible. Anybody not get a sheet last time?
I'm saying it's hard to just.
All right. Let's look at. I meant to make copies of the chi-square table and I didn't. That's okay. I want to look at the 3.5-15 on that last problem, or the last sheet that I handed out last time. So let's just read what the problem says. It says we got 15 observations taken independently, and they're taking it from a chi-squared distribution with 4 degrees of freedom. So remember again, this is our notation for chi-squared, so we use the Greek letter chi, and then of course the square. So chi-squared. Inside the parentheses is our number of degrees of freedom. So 15 observations taken independently from that particular distribution. Well, I answer the question in a second, but what kind of distribution does this sound like? If we're taking independent observations over and over and over and over again, what kind of distribution does that sound like? It sounds like a discrete one. What specific one? The Bernoulli trials is a binomial distribution, right? What's your number of trials going to be in this case? 15, right? So somehow we're going to need to convert this problem into a binomial problem, and in particular, if we read the rest of the problem, it says, what's the probability that at most 3 exceed, I can spell exceed, 7.779. All right, so there's 2 different ways we can do this in particular. Well, we're doing observations exceeding 7.779. So that's going to be our idea of success here, correct? We're doing Bernoulli. We're counting the number of observations that exceed 7.779, right? So our p, whatever our little p is for the binomial, it's going to be the probability that our observation is greater than 7.779. That's what little p is going to be, and we already said that n is 15, correct? Everybody see where that's coming from? Okay. We know that it's not just a single observation, because we'll get the single observation from looking at either the chi-squared table or using Excel, one or the other, right? We're looking at multiple observations being greater than 7.79 out of 15. So that's why we know it's a binomial distribution, but we have to use the chi-squared to get our probability of success. So if we're going to use the chi-squared table, remember again that table is on page 583, which I don't have copies of it with me, but remember that was what the table looked like, and I don't feel like logging back into the computer just to put this on the document camera. So don't be lazy. Everybody can see that from there, right? Remember again, down the left column were your degrees of freedom, and across the rows were the values that told you that the probability was less than a certain value or greater than a certain value, depending on how you read it, right? Okay. So if I go down to row 4 and go across to 7.779, I found that 7.779 value This corresponds to what it says chi squared of, if I can read it again, 0. I squared in the wrong spot. Of 0.01, no, 0.10 of 4. So remember what that point, remember the subscript and the probabilities were complements of each other, right? In the table, the value corresponds to the percentile. So you need the percentiles at the top. I know it's been a few days, we've slumped since then. But the values at the top of the probabilities, and the subscripts were the complements. It was the probability being greater than that value, right? So that 0.10 actually corresponds to this probability. So the subscript that was here in the table corresponds to that probability. And again, the idea was, if you've got the table, you've got the degrees of freedom going down the left. You had the probabilities going across the top. Equals 95. Okay. If you read across the row 4, the values in the table are 0.297. What's the next one? 0.484. And then this was 7.779. 9.488, if I read that correctly. Okay. And so on. So this was the value at the top. This was the percentile. This is a probability that a value falls less than this number, right? But right below it, they also wrote the chi squared of 0.1 of r here. So that's the probability that's greater than, is the subscript. Just remembering what the table looked like. Does that seem vaguely familiar from Friday? Okay, cool. We also could do this on Excel. So just to remind you of that as well. Maybe I'll remind you. I'll get to Excel here. So, we'd love your feedback in Excel. Well, you're not going to get it. All right. Yeah, that's 2 more that I'm going to answer right now. All right. So, remember, for your chi-squared distribution, you can just start typing chi, and all the different options for chi-squared pop up. The chi-squared.dist is the one that gives you the probabilities that you're less than a certain value. That gives you the cumulative option. Or it also will just plug the number into the PDF. If you tell it was false, remember I had the true-false option at the end, right? It also does the same thing, but for the right tail. So if you don't want cumulative, you can just do right tail to go above. Okay, that's what this one does. What we want is either the chi-squared inverse or the chi-squared inverse right tail. We want a probability, and we want it to spit back. No, I'm sorry. We don't want that one. We want the first one. Remember, the second one is we give it a probability. It will spit back what we'll call a critical value. It'll tell you the number that corresponds to having that probability being less than or greater than, depending if you're doing left tail or right tail. Right? So for us, we want the right tail distribution, right? Because we wanted the probability that we're greater than 7.779. So the x value would be 7.779, and the degrees of freedom was 4. Right? For x greater than 7.779. And it gives us 0.1, essentially. I said that for Michael's benefit. Okay. Again, if you went the other way around, if we did, just to show you how the inverse one works, We plug in a probability with the degrees of freedom, it'll give us the value. If you plug in a right tail probability of 0.1 and want 4 degrees of freedom, it tells you 7.779, essentially. The important part for this problem was that we're going to use 0.1 for the probability. All allowed to say that. But we have got a couple of ways that we can get at it, right? We can get at it through the table, we can get at it through Excel, and there are other chi-square calculators. I'd be surprised if some of your more sophisticated calculators wouldn't have it on there. There's certainly online calculators that you can find them as well. But these are 2 easy ones. Any statistical package will have it. So if you're doing R or SPSS or anything like that, it'll have it in there as well. GeoGebra has it in it, if you're familiar with GeoGebra. All these things are built in because they're well known and well used. Either today or Wednesday, we'll see why we care about the chi-squared distribution so much, depending on how quickly I get through other things. All right. Anyway, we okay with how we got the probability? And we're okay with using the table over Excel? Okay? All right. So let's go back and answer the problem because I haven't done that yet. Okay? All right. We know our P is 0.1 and our N is 15. We need to convert this now over to the binomial, right? It says at most 3 observations. So we want to compute. So if we say let y equal the number of observations that exceed 7.779, then we want the probability that y is less than or equal to 3. And the reason why we know this is binomial is because we've got independent observations taken from the same from the same distribution, and we're interested in number of observations above that value. Right? So they're independent and identical trials, and we're counting number of successes. That's how we know it's binomial. Right? So if I were to write this out in a summation notation, what would this look like?
Sum from y to
Okay. If n choose, they'll call it y in this case, right? So 15 choose y.
P-value.
Okay, which is it's 0.1 in this case to the good and good. Right, we need 3 success, at most 3 successes, which means we'll have at least 12 failures in each case. Now again, I don't know about that. Now again, we could do this plugging in the calculator, but we also can go back over to Excel. I haven't shown you this yet, so might as well. All right. If I start typing in binomial, a whole list of stuff comes up, right? If I just type in BIN, there's some other stuff that we're not going to be using, but I want to use this binom.dist function, binom.dist function. All right, so notice that it takes in a number of successes, a number of trials, a probability of success, and whether or not you want it to be cumulative, just like before. So we said the number of successes that we were interested in is 3, right? Number of trials is 15. Probability of success is 0.1. And in this case, we do want cumulative because we want it less than or equal to 3, right? So I'll put true for that. And then Excel can give us all of that fancy information. get 0.94 repeating. Is it okay with everybody?
Going back to the first part of the problem, what is that 7.779 exactly?
Oh, just a number that they could look up in the table.
Yeah.
Yeah, that was all they did. It was just a number that you were able to look up in the table. Because when this book was, well, this book is written for just being able to use a scientific calculator rather than having all the other tools at hand to be able to do these things. So they just picked a number that you could go into the table and go look it up. So that was what it was. It had no real practical value for this purpose. Now, what you're interested in, typically when you're doing chi-squared, is you're doing hypothesis testing on the variance of a population. So that value is going to tell you whether or not you think the variance is what it is, or if two populations have essentially the same variance or not. Stuff that we'll talk about next semester. Right now, we're just playing with the properties of the chi-squared distribution and getting used to it. But the 7.77. So what you're saying is that if you thought that the variance was a certain value, and you calculated what we refer to as a test statistic and got it being 8 point something, then you would know that there's only a 10% chance that you're above 7.779, so it's probably not the value that you thought it was. That's where that stuff comes in later on. That's about as vague, about as less vague as I could make it without going into more details. We'll go into the details next semester, that kind of stuff.
Find out in a few months.
You will find out in a few months. Yeah. I don't know who had their hand first.
Okay. So, like, I get how we get the numbers from the chart, but like, how does the probability of success related to like this distribution? Like, how do we, like, could you explain the conversion, how we knew that the 0.1 was a probability?
So they told us that we're taking several observations from the same distribution. So a single observation is coming from the chi-squared, and that single observation would have a 10% chance of being bigger than the 7.779. Okay, so the underlying distribution, the chi-squared distribution, is the single distribution, or the single, where the single observation is coming from. Sorry. So that probability of being 0.1 is coming from that chi-squared. Now we're doing another observation and another observation, so we're doing one after the other. We're looking for, was it above 7.779 or not? That's where we're getting to the binomial. That's where the conversion is. We're starting to do one after the other, one observation after the other. That's where it came from. Sam? That was my question. Oh, okay. Well, I answered it. Whether or not I answered it satisfactorily is yet to be determined, I suppose. But that's the idea. We okay with that? Think so? All right. Well, I'm going to assign more homework on it on Wednesday anyway. So if you're not okay with it, you'll have time to think about it. Yeah, Sam.
So if we take that same problem, but we take out the binomial part, then how would we set up that distribution? Like with the formula, with the chi-square formula, you know, from the game.
Take out which part, I guess is what I'm
Like
asking.
if you're not doing the independent observation.
So I'm only doing one observation? Then I would have just done what I did and just looking at the table and it'd be done. When I got to the 0.1, I'd be at the end of the problem. That would be it, yeah. When I get to 0.1, then I would be done. Right.
So if you were to do the same with the chi-square formula, you get 0.1?
Yeah, if you did doing the integral by hand is not possible, but if you set up the integral, we could do some approximation techniques. If you wanted just with the actual distribution, that your x is less than or equal to 3, less than or equal to, if you want to do x is greater than 7.779 using the chi-squared, that would be your integral from 7.779 to infinity of the x to the negative 1/2 e to the minus x over 2 over, what was it, square root of pi No, square root of pi.
Gamma.
It's gamma of a half, so it's square root of pi. 2 to the 1/2. Oh, no, not 1/2. No. Nope. It's 4. It was 4 degrees of freedom, so it would be 3/2, and then this would be 2.
Wait, why would it be 3/2 if it's 4?
Because you subtract a half. Oh wait, it should be cubed. Sorry, that would be what it would be. It's at -1. It should be 3.
It's R over 2 minus 1, so it'd be 4 over 2.
Oh, it should just be just 3. Thank you. Yeah, that was what it was. There you go. So that would be how you would do it by hand, which you could do in this case. Say it again. This one you can actually do integration by parts and get it. Since you got a positive integral power of X, you can do integration by parts and get it.
It's the gamma of 2, 1.
Yes. Yep. I was trying to plug in the formula and didn't do it properly in the exponent. I'm not doing it by hand. I don't want to. All right. I can. It's not that bad, but I just don't want to. All right. It's okay? Are you okay with that? That's how you would do it with the integral. I mean, I'm not going to expect you to do them with the integral. Because if I do, well, for one, if you take any odd number of degrees of freedom, you can't do the integral by hand. You can get it down to a gamma idea, but you can't do it by hand easily. And it can get nasty pretty quickly just by making the powers high. So either you'll use the table or you use Excel. All right. So the chi-squared will be an important distribution when we start talking about things next semester, and we'll use it a few times this semester, but mainly we're setting up, a lot of the stuff that we're setting up now is stuff that we're going to be using later on. So that's exactly what we're going to do in this particular section. In section 3.6, we're going to talk about the normal distribution. And in statistics, the normal distribution is the most important distribution that comes up. We're gonna talk about a very, very, very big theorem at the end of this semester that basically says that if you take your sample size big enough, everything is normal. Okay? So this particular distribution is exceptionally important in doing hypothesis testing at all. So you see the normal distribution pop up in educational statistics, in biostatistics, engineering, all sorts of places. The normal distribution will pop up if you're doing anything that has to do with hypothesis testing at all. Okay. So the first thing we're going to do is write down the ugly PDF for the normal distribution. Yes, Sam.
Are we doing students T this semester?
No, that'll be next semester. That's the name of another distribution.
It's like the normal distribution.
It's
students T. What is it?
The person who came up with the distribution published under the name of student.
Like
so it's called
student.
Yeah. That was the name he published under, so it's called students T distribution or just the T distribution.
You missed the chance to name it the Lahavi Tau distribution.
They could have.
Shut up.
They would have named it the Ruby Problem distribution. Mark would know how to say it.
If I was to ever publish a paper that would be worth people actually paying attention to it, I would publish it under Lahavi Tau, so everyone would have to call my finding the Lahavi.
The hobby. If you ever. All right. So this is the PDF for the normal distribution. This is a sigma. So is that. So this is. Let me put parentheses around it to emphasize. It's a Hershey's Kiss. Okay, fine.
I don't even know if it's that. It's looking a little rough today, Dr. Joe. People would forever have to say it.
It's okay, Dr. Joe, don't let him bully you.
All right. So this sigma squared was on the in the denominator with a 2 here. This is a mu. All right. So just to emphasize, the mean here is mu, and the variance is sigma squared. Right. The idea here behind this distribution, ignore the mu, ignore the sigma squared. If I just look at this particular function, and I'm not as worried about the, oops, for my squared, not as worried about the constant out in front. If I look at that particular distribution and think about what the graph has to look like, well, let's look at the exponent. If x gets really, really, really big, I square it, it gets really, really, I square it. Big squared becomes big. Now there's a negative in front of it, so it's going to be big negative, right? No matter if x is positive or negative, right? Exponent is going to be big negative, this is going to go to 0, right? So the farther you go out in either direction, the smaller the graph gets, right? The closer the graph gets to the x-axis, right? The highest point will be where? Where? It'll be 0, right? That's as big as it could possibly get. So your graph, be confident, Megan, you got it. All right. Goes up, comes back down, hits here.
Throw your pen at it.
No, it costs a lot of money though. So.
I was just curious to hear.
I'll catch it. Throw some
Yeah,
chalk at
throw
it.
chalk.
Is that right?
Throw chalk eraser.
My accuracy is awful. I'll hit somebody else. Like Ashlyn, for example. Ashlyn didn't do anything to get hit. She's just sitting there quietly. Okay. All right. We'll hit the x-axis. If I consider the constant out in front, it'll hit the the y-axis at 1 over root 2 pi. So you've probably heard of bell-shaped curve. That's what your normal distribution is, that bell-shaped curve idea. The reason why we need that 1 over square root of 2 pi in front is because the area, if I ignore the constant out in front, just do the area of this one, you get square root of 2 pi. Remember we got the square root of pi part that popped up, square root of pi over 2 that popped up when we did that integral the other day for gamma. When we did the derivation, we had the double integral, that iterated integral pop up, remember?
Yes.
Yeah, okay. Remember when I said there was only one quadrant?
Yeah.
And we had that pi over 4. It was squared though, right? We had a pi over 4 and a pi over 4. We did the square root of it, I have square root of pi over 2, each of the 4 quadrants. So that comes up with square root of 2 pi. Wow. Yeah. Anyway. So that was where that comes from, that idea. So that's why there has this particular constant out in front, is to make it be a PDF and make it equal to 1. Okay? When I change, if I do a shift of the mean, shifting left or right doesn't change the area, right? So all this minus mu here is just making it so that you can adjust where the mean is, right? That's all that's doing. This sigma squared, of course, is changing the scale, right? If I make this bigger, it's going to be more spread out. If I make this smaller, it'll be more squished in. Remember, when you do horizontal stretches and strings, it does the opposite of what it does out in front, right? Bigger number makes it taller. Smaller number makes it flatter. Inside is the reverse, okay? So if I want to make this get wider, I would need to make the constant that I'm multiplying smaller, which dividing by bigger numbers makes the constant smaller that I'm multiplying by. So the bigger the variance gets, the wider it gets. The smaller the variance gets, the narrower it gets, which makes sense, right? We think about just variance being a measure of spread. Bigger numbers should be more spread out. Smaller numbers should be more compact. And the reason why this sigma is out in front here is because I need to adjust to make sure that my area stays 1. That's going to be a PDF, right? So when I put the variance in here, I'm going to put a sigma on the front to keep everything equal. Think about what you would do if you did a U substitution, right? If I did a U substitution, the 2 would come down in front, so we cancel that 2. Right? Agree? Okay, so that would be why I would need this sigma in here to adjust for the area. Yes, Sam?
That's the standard deviation, right? Or is it?
The one that's out in front is the standard deviation, yeah, because it's the square root of sigma squared. Yeah, as a matter of fact, you'll see other books write this as sigma squared inside the radical, rather than a sigma outside the radical. They have the sigma squared inside the radical? Yeah. It bothered the authors too. They put it outside. Okay. All right. So this is your normal distribution. Now, again, we've got that e to the negative x squared piece in there. So it's really, 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 really hard to try to evaluate probabilities exactly using a normal distribution. So there's a couple of ways to get at it. One is with a table in the book, which I'll do more of that next time because I don't feel like hooking up the document camera again. And then, or we could also use Excel, which I'll show a little bit about that when we actually do some problems. So I'll show you how to do, like I said, next time I'll show you the table, and today I'll show you a little bit with Excel when I get to do some problems here. Besides the mean and the variance, of course, one of the things that we would like to know about the normal distribution is its moment generating function. There are reasons why we like the moment generating function besides the fact that we get the moments.
For the next test, is the first sheet of the test going to be the equations again?
Yep.
Is that a plus sign?
In the middle, yes.
And they use another variable besides t.
No. 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 No.
T.
No.
T.
Michael feels very strongly about the fact that this isn't this.
That's why my T's have little tails on them. So you can tell the difference between that and a plus sign. It's also why when I write a Z, it has a line through it, because you can tell the difference between that and a 2. I mean Z. I'm not British.
I like
All right. Sailboat?
Yeah.
Smiley face?
I like using sailboats for variables.
Like that? Yeah. Okay. And then I can make it a smiley face.
The bottom just looks like
Haley didn't even pay attention. I did that just for her. I said I made it a smiley face.
It looks like a really bad.
It's like a
Oh wait, now it looks like a pumpkin.
Yeah, I was going to point out it's a Halloween, right?
What's wrong with his head?
It's still attached to the vine.
Why is the right side of his head gone?
Somebody kicked it.
Rip. Oi! In the woods, there's like a broken pumpkin on the ground.
Oh my gosh, there's like 15 of them.
Oh, is there?
All right.
Sad.
Oh, goodness. Okay. So,
Sad day to be a pumpkin.
sad day to be a pumpkin. All right.
October 31st is the worst day to be a pumpkin. Honestly.
You know what the worst day to be a
I feel
turkey
like
is?
November 1st is the worst day to be a pumpkin, because it's like Halloween's over.
No, I actually keep mine out for Thanksgiving.
I usually switch to rewards for Thanksgiving. I switch the pumpkins out for actual rewards.
Oh, well, aren't you just a badass?
Yeah,
All
I
right.
think I am.
So, when we're doing problems with the normal distribution, again is a continuous random variable. We typically, with continuous random variables, random variables want to know if an observation is less than a value or greater than a value or in between two values, right? Which if we have the CDF, we know the CDF talks about being up until a certain point for the probability, correct? Now again, when we do the normal distribution, we can't do an antiderivative of e to the minus x squared. Can't find that in closed form. So when I talk about the CDF, again, the only way you can really write it is in integral form. But we use the normal distribution enough that we actually give a name to the CDF, a function name for it, without actually writing it as an integral. So when we write capital phi of x, this is the probability that capital X is less than or equal to little x when your x is normal. Sorry. Nope, not mu sigma squared. It has to be 0, 1.
What is the end zone?
So that means normal distribution, mean 0, standard deviation 1, or variance 1.
So it's like a z-score.
Yeah, that's exactly right. That's exactly what it is. So we refer to this particular normal distribution as the standard normal distribution. So in the standard normal distribution, your mean is 0 and your variance is 1. So if you've done any statistics at all, or done anything with normal distribution, one of the first things that you do in a problem is convert your normal distribution that you're talking about over to a normal distribution that has a mean of 0 and a standard deviation of 1. Yes, Grace?
Is it the standard deviation one or variance one?
But both.
Oh.
All right. So our standard normal is with mean 0 and variance 1. I should be saying variance more anyway, because when you write this notation, the mean goes first and the variance goes second when you write it that way. All right, so when I say the CDF of the normal distribution, really what I'm talking about, this thing is the CDF of the standard normal. And when you look at your table in the back of the book, those are all values that correspond to the CDF of the standard normal distribution. And that's the only thing that you need, because anytime, if you've done, like I said, if you've done any statistics before, one of the first things you do is convert the normal distribution you're talking about over to the standard one. If you've heard z-score before, it's exactly what you do, right? Okay? So, as the theorem goes here, it says that if x is normal on mu sigma squared, then z equal to x minus mu over sigma is normal 0, 1. And that's how you do the z-score in. So let's talk about why this is true. And the main reason why I want to do this is we haven't done a lot of practice with what we're about to do, and we're going to do it a few more times over the course of the semester. And this is generating a PDF from the definition of the CDF. We've done it a couple of times, but let's talk about it in this case. If I want my CDF, oops. What or what?
G.
It's a G.
What world is that?
Dr. Joe, I'm surprised you put up with this.
There, is that better?
That's a big difference.
It's the same as the way you guys.
Maxwell did not accept that. No.
Okay. All right. So this is how we would define the CDF for Z, right?
Yeah, the train agrees.
Plug in what Z is equal to in terms of X, and then solve this for X. We have X is less than or equal to sigma times Z plus mu, right? Now, what did we do? Why are we doing this? I'm trying to find the P. I'm saying that this has a distribution that is normal 0, 1. So my goal is to figure out what the PDF is, so that I can see that the PDF is the PDF for a normal distribution with mean 0 and standard variance 1. All right? Okay. So I started with the CDF because I really have nowhere else to start. The only thing I really have is a relationship between my Z and my X. So I started with my CDF, plugged in the formula, and then solved for X. This is now a statement about the CDF of X, right? Right? So this is equal to capital F of sigma Z plus mu, where this is the CDF of X. Now, how do I get from CDF to PDF? Take a derivative, right? So, if I want the PDF, I'll write my G very carefully.
I'm glad you went extra careful this time.
There, is that better?
Yeah, you just
Okay.
put a lot more thought into this G. This one actually feels special.
Oh,
I'm
good.
getting abused.
It's fine. All right, it's fine. I need to take the derivative of this. When I take the derivatives, I have to do the derivative of the outside function and then multiply by the derivative of the inside, right? Chain rule, correct? I'm differentiating with respect to the Z, so the derivative of the inside is just going to be the sigma, right? Okay? But we said the derivative of capital F is going to be our little f. Which we know that looks like 1 over sigma times the square root of 2 pi e to the negative something minus mu squared over 2 sigma squared, right? What am I going to plug in here where I left the blank?
Sorry.
That was a lot of attitude.
My attitude definitely did come out.
Who knows? And honestly, who really gives a... Never mind.
I should give you a break today because my being after me.
No, it's fine. What's going to go in for the X?
The sigma
Mu, 0.
plus
Oh yeah, that.
That! This was an X, right? In the PDF, this is an X, right? What has the X been replaced with? The sigma Z plus mu, right? It wasn't a trick question. Grace's attitude aside, it wasn't a trick question. All right, so let's look at that exponent. What's going to happen in the exponent?
The U is gonna go away.
The mu goes away, right? Those cancel each other out. Then what happens? The sigma squared, get a sigma squared, Z squared. The sigmas will cancel out, right? And then out in front, we also have the sigmas cancel out here too, don't they?
Oh my
Whoa, would
gosh.
you look at that?
Would you look at that? We get down to 1 over square root of 2 pi e to the minus Z squared over 2. Does that look like normal 0, 1?
No.
Okay, good. I'm glad it didn't. Did everybody else's look like normal 0, 1?
Well, there's a Z instead of that.
Ah, there it is.
Oh, the letter matters?
Yes.
Of course it does. All right. Anyway, so this shows that we really do have a normal 0, 1. So this transformation of the normal random variable we started with will always convert to a normal random variable, mean 0, variance 1. So this is why if you've seen any statistics at all in any other class, anytime you have a problem that involves a normal distribution, the first thing you do is calculate z-scores. That's what we call this, right? when you do x minus the mean over the standard deviation, you call it calculating a z-score for a particular value. Because what you're really doing is you're changing the observation from one that comes from an arbitrary normal distribution to one that comes from a standard normal distribution, so that you can answer all of the questions in the context of standard normal distribution. That's the whole point. Okay. All right. Questions on that? Because we're going to do one more thing with the standard normal. And then we'll do problems next time.
Wait, you said you have to get to why chi-square is so important.
That's what I'm doing.
I mean, chi-square is important, or normal distribution? I thought we were done with that.
They're all important.
It's only important if you call it chi.
That makes it very, very less important.
Yeah, if you call it chai tea.
Chi-t distribution.
All right. So if you take the standard normal distribution and square it, you get a chi-squared distribution. Why is this relevant to variance? Well, think about how you do variance. What do you calculate? You do expected value of the variable squared, right? And then subtract off the expected value of the variable quantity squared. Well, if it's standard normal, what's the expected value of the variable? 0, right? So the variance is just the expected value of the variable squared, right? So when I'm looking at the expected value of the variable squared, I'm looking at the distribution of the variance. That's what this is talking about. That this really is a discussion about the variance of a normal the distribution of the variance if you're doing a random process. So this is why we care about chi-squared. So let's talk about why this is true.
Is that chi-squared with 1 degree of freedom?
It is chi-squared with 1 degree of freedom, yes.
We're gonna do this by induction, Dr. Joe.
What's that?
I said, are we gonna do this one by induction, Dr. Joe?
No. All right. So let's say that W is a letter I'm going to use here for the variables, for lack of a better letter. Same idea. I need a probability that z squared is less than or equal to some W, right? Well, if I do square roots, what does that say z would have to be in between? If z squared is less than or equal to W, what does z have to be in between? Negative root W and root W, right? You agree with that? Now z again is a standard normal distribution, so we can actually write this in terms of an integral.
Why can we write this in terms of an integral?
Because I said so.
We're just going for it?
We're just going to sit there.
Z is a normal distribution, right?
Yeah.
So it's a continuous distribution, so that's exactly how we do probabilities.
Okay.
Right?
I agree.
You agree? Okay. She doesn't? All right. What? What?
I was just gonna start an argument with Michael for the sake of turning.
Oh, okay. Well, good. Let's start an argument with Michael. That's fine. He's been very argumentative today, so you might as well.
Ouch.
All right, so that would be how we would calculate that, correct?
Yeah.
We agree? Okay. No, this function is symmetric about the y-axis. It's an even function, right? If I plug in negative z, I'll get the same thing as if I plug in z. This is symmetric about the y-axis. This interval is also symmetric about the y-axis.
So it equals 0.
No.
Well, that's awkward.
Oh, that's odd function.
Yeah. I could replace it by double and put a 0 on the bottom, right? I didn't. I split it. It's an even function. I'm going about an interval that's symmetric about the origins.
I was following you, and then.
Michael
for whatever
distracted you, I'm
reason-
sure.
I didn't do anything. She
All right.
just took a sharp turn off the.
All right. If now we want to get to the PDF and the CDF, what do we have to do? Sorry, the other way around. We want to get from the CDF to the PDF, what do we have to do? Derivative. If I take the derivative of this, I've got to put that's why I put a constant down here, right? I got to put this in for the variable, and then take the derivative of this by the chain rule, right? Derivatives and integrals cancel, correct? This goes in for a variable, but this is a function of w, not just a w, right? So the derivative will be 2 times 1 over root 2 pi times negative root w squared over 2 times 1 over 2 root w. Oh, I do need an E, sorry. It took a power. I was like,
Either way, everybody comes
I forgot to write the E down.
It's been a long day for all of us.
All right.
Why is that E
Yeah,
so flat?
but it
All right, let's do this now. This I can rewrite as w to the 1/2 minus 1. W, the square root of w squared just becomes a w. This is 2 to the 1/2 under the radical here. I have square root of pi. What did we say was equal to square root of pi the other day? Gamma of 1/2.
Wait. Oh, we did that.
Why did I write it like this? What are we trying to see? That it's chi-squared. Does that look like a chi-squared PDF?
Yes, it does, Dr.
Yes,
Johnson.
it does.
Chi-squared.
It looks like a chi-squared PDF. So this is
Chi-squared.
chi-squared of 1. All right. Have a good one, everybody. Hopefully you're just as rambunctious on Wednesday.
Wednesday, all
Next time, we actually got more done today than